Oh, good morning, everybody. So we're continuing our discussion in the structures notebook. In the previous lecture, I told you that C uses pass by value to pass values back and forth from a function. The same is true with structures. So if you pass a structure to a function or return a structure from a function, what happens is you get a copy of the structure when you pass the structure to a function, and you get a copy back when you return a structure from a function. So what does that mean? If you're always getting a copy, that means if the function modifies the copy, the caller's structure doesn't actually change. So it's similar to the original max function. If you pass two ints to a function and you want to, the swap function, and you want to swap their values, it doesn't work, right? You get a copy of the values passed to the function. So here we have a structure. We have a function called move. It takes in a 0.2 structure, and it moves it by 100, 100. So it just adds 100 to the x and y coordinates of 100. If you print out the value of t, or the x and y members of t, you will indeed see that the values have increased by 100. Now the problem is, if you return t, the returned structure is in fact the original, or its coordinates are the coordinates of the original structure plus 100. The problem is that you're returning a new structure back to the caller. Right? So here the caller has a structure p. Its coordinates are 1 and 2, right? And the caller wants to move p, right? And so if you just look at the declaration of move, it looks like it actually changes, or it looks like the intent is to move the point t, right? So here you pass in p, right? The function gets a copy of p, so t up here now is a copy of p. It's as if you had written t equals p here. The function changes the copy and then returns the copy back to the caller. The caller actually gets back a copy of the copy. Right? So here, the first time you call move and then you print out the coordinates of p, right? You'll see that p in fact doesn't change its coordinates. So you run the little program here. So p before the move is 1, 2. Right? Inside the function, it does in fact look like the point has changed its coordinates. Right? After the function, the original point has not changed its coordinates. Right? The thing that's changed its coordinates was the copy. Right? So if you want to use this kind of function, or if the caller wants to use this kind of function to move a point or to modify a structure, then what the caller has to remember to do is that they have to remember to assign the result back to the structure. Right? So here we're assigning back the result of move back to p. Right? If the caller forgets to do this, their point doesn't actually move. Right? But when they do this, right, the p after assignment is in fact 101 and 102. Right? So one of the problems with this particular function is that you've made one copy of the structure to call the function. Right? So pass by value causes one copy to occur. Right? Return by value causes a second copy to occur. Right? The assignment here, the assignment on this line here causes a third copy to occur. Right? And so if your structures occupy any significant amount of memory, this is a very inefficient way to do things. Right? A better way to have written this function would have been to take the input as a pointer to a structure. Right? Possibly. Right? If the intent is to change the caller's point, then a better way to have written this is to have taken a pointer to a structure. Right? That allows the function to actually modify the structure object owned by the caller. Right? No copying occurs except for the copying of the pointer, which is cheap. Okay, and the last thing we need to say about structures is that you're allowed to have arrays in a structure. You cannot have a variable length array in a structure, which is problematic. Well, it's not, it's a limitation of the language. It forces you to do things in a different way. Okay, so here we have a structure. Now remember, arrays in C, they don't remember how big they are, which is super inconvenient. And so you might say, well, I can just make a structure, and inside that structure I can have an array, and I can remember how big the array is. Right? So you make your own structure called int array, right? The first member of your structure is the size or the length of the array, right? And then you want to make an array having that size. So that would be the natural way to write it. Unfortunately, the language doesn't let you do this. The reason it doesn't let you do this is because the size of the array is a variable, right? So in other words, it's not, you cannot determine the size of that underlying array at compile time, right? And what does that mean? It means you cannot determine the size of the structure at compile time, right? You know that there's something of size t, so you know how big that is, right? You don't know how much memory this occupies because size can be variable. And so the size of the structure is not determinable at runtime, which is not allowed in C. Right? All objects their size must be must be able to be determined at runtime, at compile time. Sorry. And so this doesn't work, unfortunately. Now C does allow you to do something like this, which looks funny. And so this is called a flexible array member. So if you want to implement this sort of structure like int array, you can still keep track of its size, and then you can make an array whose size is unspecified. And so this is allowed. What ends up happening here is that this thing becomes a pointer. So the other way to do this would be to just make a pointer anyway. And so if you want to learn more about this, there's several links here that tell you additional information about structures. It's not important that you know this stuff here for the purposes of this course. I don't even think we're going to use a flexible array as a member of a structure in this course. We're going to use a pointer, but we're not going to do this sort of thing, right? If you look at this sort of thing, so if you've taken and completed 124, and you look at this thing here, this sort of looks like the beginning of a list, right? An array-based list. You're going to remember how much capacity is in the list, right? You're going to remember the elements of the list, right? If you wanted this to be an actual list, you would need to record how many elements are in the list. Right? And so this is how we're going to implement strings and possibly lists and other data structures later in this course. Except this is going to become a pointer. All right, so that's it for the structures notebook. Any questions about structures? Super. Yes?
I always heard C is really fast.
Yeah.
Is it because of like the pointers?
So the pointers are one part of what makes the language fast. Yeah. The real reason C is fast is because the language is very small, right? All of its statements and declarations, they all approximately map onto actual machine instructions. So when you write something like some int a plus some int b, underneath the hood, the compiler is calling the CPU instruction that adds 2 ints. Yeah. And so almost every operation, every fundamental operation basically maps onto a machine instruction that's one or a small number of instructions long.
No middleman.
Yeah, there's no middleman. So if you want to do anything fancy, you got to do it yourself. And now you pay the price of whatever it is you're doing, right? Languages like Python and Java, they impose those on every programmer. Right? That's why C programmers hate languages like Python and Java. Okay, the next notebook is arrays. So this is where we really go into detail into using pointers. And the reason we have to do this is because arrays and pointers, there's a close relationship between the two in the C language. The first part of this notebook is all review, because I've already talked about it before. And so I'm just going to quickly go through the early part of the notebook, and then we'll slow down when we get to the about a third of the way through. Okay, so just to remind you, arrays and in C and Java are pretty similar, at least on the surface, right? The syntax is basically the same. They both represent the same thing, right? They are a contiguous sequence of objects all having the same type, right? Contiguous, again, remember that means they are, each object is beside one another in memory. The capacity, or the maximum number of elements in an array, can never change during its lifetime, right? So you can't actually resize an array. Whenever you quote unquote resize an array, what ends up happening is you end up making a copy of the array. In both languages, the array type is characterized by its element type, right? So an array of int is characterized by the fact that the elements are ints. And of course, you use the square brackets to access the individual elements. One of the big differences between C and Java is that Java allows a 0-length array. So you can have an array of length 0 in Java. C technically does not, but most compilers will let you get away with it. So technically, you are not allowed to allocate 0 memory for something in C. Another big difference is in Java, you can assign to a variable that is an array variable. Right? So you can write int square brackets a equals new int blah 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 blah, and then on the next line you can write a equals new int blah 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 blah. Right? You can't do that in C. So as soon as you have an array variable, you can initialize it, but that's all that you can do with it. Right? You can't assign to it later at a later point. The other big difference is that there's no index bounds checking. That's why it's in bold. Right? So if you try to access an element of an array using an invalid index, an invalid non-negative index, you don't know what's going to happen. Well, you know what's going to happen. So what's going to happen is the C will try to go into the element at that location, even though you've gone past the end of the array. Right? Depending on what that operation involves, your program can do anything. So it may crash, it may keep on running, and we saw an example of that a few lectures ago. Okay, so arrays always degrade to pointers when the array is passed to a function. So you can't actually pass an array to a function. What ends up happening is you end up getting a pointer to the first element of the array. Right? Similarly, when you can't return an array from a function. Right? If you want to return an array from a function, you have to return a pointer to some element in the function. Sorry, you have to return a pointer to some element in the array. Typically, you return a pointer to the first element of the array, but that's not required. Okay, so we know how to declare and initialize an array, right? So that's declaration. Where's initialization? Oh, I don't have initialization. So that's declaration, right? We have an array of size 3. You don't know what elements are in the array, right? There are 3 elements there. You just don't know their values, right? Whatever memory happens to be sitting in that array is the array of those values. Is the value of those elements. Right? There's assignment to the individual elements, and of course, if you print out this array, it's 1, 2, 3, right? What happens? Okay, so here's an example of what happens when you use an array and you don't initialize it or set its elements, right? Whatever values are sitting in memory, those are the values that you get. So here I get some random values, seemingly random values, right? Every time you run the program, it looks like different random values. So be careful if you create an array, right? If you need the values of the element to be initialized for some reason, you have to initialize them yourself. Right? How do you initialize them? Well, you can use an initialization list, but this is only practical if the array is short, right? Otherwise, you typically end up writing a loop or a function that fills in the elements of the array. You are not allowed to try to insert more elements into the array than there is size of capacity in the array. Right, so here we're trying to initialize an array of length 3 with 5 values. This is not allowed. I think the compiler the compiler catches this one. If you have fewer initializers than there is capacity in the array, then the remaining elements of the array are left uninitialized. So again, be careful with this one as well. Right? Sorry, there's a number missing here. X5. Okay. So here's an array of length 5. I'm going to initialize the first element to 3. The remaining elements, we don't know what value they're going to be. Here we get 3, 0, and, oh, sorry, that was supposed to be a 3, I guess. So here we get 3, 0, and 0. So again, it may seem to be the case that C is 0 initializing the remaining elements, right? That's not guaranteed by the language, right? It's happening in this particular case only as a consequence of my particular compiler, my particular hardware, et cetera, et cetera, et cetera. Okay, so remember that strings are just arrays of characters, and so all the limitations that you have with arrays, you now inherit when you work with strings. Right? Don't forget, it's your responsibility to stick the null terminator into the end of the string. Right? So you have to indicate the end of the string using the numeric value 0. Right? As a character that is as a character literal, right? That's single quotes \0. Right? Don't use single quote 0. That's the character 0, not the numeric value 0. So we'll just skip over this because we know about that already. Finally, we have this thing called a const array. So you can mark an array as being const, right? So remember what the keyword const means in C. It means something is, it's trying to indicate to you that something is a constant, or its value is read only. Right? So the question is what happens when you have a const array, right? Is the array variable itself constant, or are the elements of the array constant? And it turns out it's the elements of the array that are constant. So here, const int x3 says you have an array of size, you have an array x of size 3, right? Its values are 1, 2, and 3, and you cannot change those values in the array. So run that, right? So I can get the value out of an array, right? The elements are read only. But if you try to set an element in the array, right, your compiler will indicate that as being, oh wait, the GCC, yeah, this compiler is indicating this as an error, right? And it tells you error assignment a read-only location x1, right? So const array means the elements themselves are const, right? Incidentally, you already know that the array itself is constant, right? That variable x, you're not allowed to reassign to it anyway. So once you've created the variable x, it always refers to the same array. Okay, assignment to, oh, we know that assignment to an array variable is not allowed, right? So if you try to write x equals y here, you run into a problem, right? The compiler flags that as an error. It even tells you assignment to expression with array type, right? The big problem here is with strings, right? If you have two variables that that are strings, they're just arrays of characters, right? And that means you can't assign a string to a string, which is annoying, right? You would really like to be able to write this, especially if you have to work with strings a lot. You have to get used to the fact that in C you can't do this. You have to basically copy the characters of one array into the other array, right? So you can write your own little loop like this. So here I'm going to copy 10, 11, and 12, x, yeah, 10, 11, and 12 into x, right? And this works exactly the way you'd expect it to, so that prints x, right? If you want to copy an array though, you kind of want to avoid writing these loops. Instead, you should rely on this function called memcopy. Right, so whenever you want to copy a chunk of elements from one array into another array, memcopy is the function that you should consider using. So it's defined oddly enough in string.h, which seems weird, but that's where they put it. Okay, so how do you use this thing? So this function has to be able to copy any kind of array, right? And so what that means is that when the creators of the language specified the arguments or the parameters of the array of the function, right? What type are they going to use to indicate that you're copying an array of int, for example? So the answer is you don't, right? You instead use a void pointer, right? So remember, a void pointer can point at anything. And so this lets memcopy copy any type of array, right? Or more precisely, it lets you copy any chunk of memory, right? So the destination, this is a pointer to the, if you're thinking about copying arrays, this is a pointer into the array where you want to put the information into, right? So it could be the first element of the array, it could be the 10th element of the array, right? So you can insert into the, copy into the middle of another array if you want to, right? So this is a pointer pointing at the element where you want to start writing values into, right? Source is a pointer to an element where you want to start copying from, right? Count is the number of units of memory that you want to copy, right? So the number of bytes of memory. Right. Okay, so here we have x and y. Right? I would like to copy, what am I doing here? I'm copying, I think, the contents of y. Source is y, yeah. So I'm copying the contents of y into x. Right? So I'm going to use memcopy to do this. So I need a destination pointer, right? So the destination pointer is where would I like the elements to start going into, right? So my destination here, I've written it a funny way, right? I've written it as the address of x0, right? You wouldn't normally write it this way, but you can write it this way. So I've written it as the address of x0. So that is the address of that element there, right? So that's where I'm going to start copying into. Source is where I'm going to start copying from. So I've written that as the address of y0. So there's y0, so wherever that is in memory, that's where I'm going to start reading from. Right? Now remember, the language says it arrays, the elements are beside one another in memory, right? And that's why you can actually write this memcopy function, right? You know that if you copy the number of bytes equal to the size of that int, right, and then you copy the number of bytes equal to that int right beside the other element, right, you're going to get the next element, right, and so on and so on and so on and so forth. Okay, how much memory do I want to copy? So you have to remember this is how much memory you want to copy, right? It's not the number of elements you want to copy, right? That name count is super deceiving, right? So it's how much memory do you want to copy, right? So if you're copying an array of int, you have to remember I want to copy 3 ints, right? How do you calculate how much memory 3 ints occupies? Well, it's 3 times size of int, right? If you were copying an array of double, you'd write 3 times size of double. Right? If you're copying an array of car, you could just write 3 because the language says size of car is 1. Okay, so pointer to the memory location where you want to start writing into, pointer to the memory location where you want to start reading from, total amount of memory that you would like to copy. Right? And so when you run this, you get x is, implicit declaration. Include string. Okay, and so there you see that x is in fact 10, 11, 12. I'm just going to jump ahead quickly. Okay, so in this example here, I've started copying from the front of one array, right? And I'm copying into the front of another array. So this effectively copies one array into the other, right? But there's no requirement that this be the front of an array. There's no requirement that this be the front of another array. Oh, notice that this is a const pointer. So this is actually trying to, this is memcopy's way of trying to tell you memcopy will not change the elements pointed at by source, right? So it's not going to change the source array. The destination array obviously is not marked as const, right? Because you have to write into the destination array. All right, so here's an example where I'm going to copy some elements from the middle of one array into the middle of another array. Right, so here's x, it can store 6 doubles, y can store 10 doubles, right, and I've initialized both arrays. All right, so it looks like I want to start copying the elements starting at the 5th element of y, so at index 4. So I'm going to start copying from here, right, so the address of y4. Right, and I want to start putting them into x at index 2, so starting here. Right, so that's where I'm going to start copying into, and it looks like I'm going to copy 4 doubles. So if I've read this right, I'm going to copy those 4 values into x, overwriting those 4 values there. Right, so let's see if I actually got that right. Of course I didn't include string. Oh, sorry. And it does in fact look like I got that right. Right, so I got 0 and 0, and then 14, 15, 16, 17 in x. Right, and you can play around with these numbers all you want. Right, so if I wanted to start reading from the 11, you would just change that to 1. Right, and if you wanted to start writing into the front of the second element of the array, you would just change that to 1. Right, run that, and you get 11, 12, 13, and 14 in the middle of x now. Right. Okay, so the fact that you have to pass in the size of the amount of memory that you want to copy means that it's very easy to copy or to try to copy too much memory. Right. So for example, if I can make my source point at this element here, right? So that's y9, right? And now I'm going to try to copy 4 elements out of this array starting here, right? And there are no more elements in the rest of this array. So there's 3 elements that we don't have that don't actually exist in y that we're going to try to copy into x. Now the problem here is that in C, this function here isn't checked, right? There's no way for memcopy to actually determine, right, are there actually enough elements in y to copy, right? Remember, arrays in C, they don't remember how big they are. And you don't even have an array here. You're actually passing in a pointer, right? So there's no way for memcopy to check, is this going to cause a problem, right? Am I going to try to copy past the end of the array? And so the responsibility of making sure that you're copying the right thing lies with the programmer here. The language says anything can happen if you call the function this way. What happens? Well, we get something weird happening, right? So we copy the 19, which is good, right? Now it looks like the other elements of the array have been unchanged, except this one's now -0 instead of 0, right? Also, we're only printing out 6 digits, so this number might in fact be something small. It's just that the extra digits might be way down here past the, right, somewhere out in the 9th or 10th decimal place. So we don't actually know that these are 0. And so something funny has happened, right? It has in fact copied a bunch of memory. So however much memory down here that I need for 3 more doubles, memcopy has just blindly copied, right? I have no idea where it's gotten that memory from, right? Other than it's the memory past that 19. Right? If you run it again, I don't know if you get the same result or not. Okay, so now you get a different result, right? So now that was what used to be -0 is now just a regular 0. Right? So you have to be careful when you're using this thing, right? You have to make sure that the memory that you're copying from actually exists. You have to make sure that the memory you're copying into actually exists, right? So for example, if I try to write into y starting at the end, so that's 0, 1, 2, 3, 4, 5, right? I'm now going to try to write 4 values starting here. So I'm going to write 3 other extra values past the end of x. And again, anything could happen. In this case, you get you get the 19. The program doesn't crash. It seems to run just fine. But you don't know what's happened to the memory of the program, right? You don't know if you've overwritten y or something else funny has happened, right? It seems to work. It's not actually guaranteed to work. Okay. So you can also use memcopy to copy a string if you like. You don't have to. The problem with using memcopy to copy a string is you have to remember to copy the null terminator, right? So if your length of the string is 5, you have to remember to copy 6 elements to get the null terminator into the string. So instead of using memcopy, you should use string copy to copy a string. String copy knows to copy the null terminator for you. Okay, so array pointers, there is a close relationship between the two, right? And so the relationship between the two is the following. So if you use just the name of the array somewhere, then as far as C is concerned, that's equal to a pointer to the first element of the array. Okay, so here's our array, right? So it's an array of 3 doubles. Somewhere in the program, if I use the name ARR, right? C considers that to be a pointer to the first element of ARR. So it considers it to be a pointer to that 1, right? So in other words, right, I can take the address of the first element of the array, right? I can store that in a pointer, right? I can now test, is P equal to ARR, right? So remember, this is a pointer comparison, which we learned about in the last lecture. Right? So remember what pointer comparisons do, right? They compare the values of the 2 pointers. So in other words, they compare the memory, what memory address is stored in P, right? And what memory address is stored in ARR. If they are equal, then P and ARR both point to the same thing, right? So the language says, when you use ARR on its own, that's equivalent to taking a pointer to the first element of the array. So this should print out P equals ARR. And it does. Right? So instead of writing star P equals address of ARR 0, you can just write star P equals ARR. Do I do that somewhere? No. Right? So in other words, you can just do that. And as far as the compiler is concerned, that's perfectly legal. So this compiles and runs without any warnings whatsoever. Right? So the name of the array and the address of the first element of the array, they are the same thing. Yes?
In practice, for readability's sake, isn't it better to put the first option and not just put array?
Yeah, so most programmers are lazy, and so they will always write the name of the array. So experienced C programmers will typically write the name of the array only. They won't write address of ARR 0. If you For the purposes of this course, it doesn't matter what you write. So if you want to always be clear, right, to yourself in particular, right, I'm taking the address of some element in the array, write it as address AR0. It's perfectly fine. Yep. Okay, and so that means you can do something that looks like assigning an array to a pointer, right? So here, for example, I've got my string, right? Strings are just arrays of characters, right? I have a pointer, right? And I can now write p equals str, right? So this says that p is a pointer to the first element of str, right? So it's a pointer to the first c, right? You can dereference the pointer, right? Now you've got a pointer into the array, right? So now you can dereference the pointer, right? So I can write star p, right? What happens when you dereference the pointer? You get the object being pointed at. So you can actually get the c that's sitting inside this array, right? That means you can also assign to that via the pointer, right? You can write star p equals lowercase c, and that will change the element of the array, right? So if you run that, right, you get sys220. When you look at the first element of the array using the pointer, right, you get the c. Okay, so you can, now remember, str is a string, right? And I told you you can't assign to array variables, right? So you're not allowed to write str equals something later on, right? We've already initialized str, it's an array variable, I cannot assign to an array variable. You can assign to a pointer though, so p equals str is just fine here, right? So here, I've got str, right? I've got my copy, right? So remember, I know copy equals string is not going to work, right? If I try to write that, the compiler is going to flag that as an error, right? Now the question is can I cheat using a pointer, right? So can I write car p equals str, right? Which we know we can, right? I can take a pointer to the first element of the array, right? Can I then write copy equals p? Right? Because again, copy is just a pointer to the first element of the array, right? So can I assign a pointer to another pointer variable? The answer is no, right? So the language does know, right, that in fact copy is an array variable, right? Because that's how you declared it back here, right? So you can't try to cheat this using a pointer like this, right? There's no way for you to get around the problem that you can't copy a string or another array, right, without using a function of some kind or writing a loop. So that doesn't work, unfortunately. All right, so if the name of the array acts as though it were a pointer to the first element of the array, right? So the question is, well, I get the first element of the array, that's easy. Can I get the second element now using the name of the array, right? And not using square brackets, right? Or can I get the last element of the array, right? Or can I more generally get the nth element out of the array, right? And so of course, you can always use the address of operator. Right? So if I want a pointer to the 2, right, I know where the 2 is. It's sitting at index 1 of the array. Right? I know how to use the address of operator, so I can just take the address of the first element, the second element of the array. That works just fine. Right? Unfortunately, again, programmers are lazy, so we don't want to have to write ampersand ARR square bracket 1, right? And so pointer arithmetic shows up now. So you can do pointer arithmetic if you have a pointer to an element of the array, right? So if we have p and it points at some element of the array, right, then p plus 1 is a pointer to the next element in the array, right? P plus 2, pointer to the next element of the array, right? And so on and so on and so on. P minus 1 is a pointer to the previous element in the array, assuming it exists, right? So more generally, if p is a pointer to an array element sitting at index j, right, then p plus I is simply a pointer to the element at index j plus I, right? P minus I is simply a pointer to the element sitting at index j minus I, right? So add something to a pointer is like shifting the index to the right. Subtract a value from a pointer, that's like shifting the index to the left, assuming those elements of the array actually exist. Right? Now, how do I get the element sitting at that location? Well, you just dereference the pointer. Right? So star round brackets p plus I, gives you the element sitting at index j plus I. Right? P minus I, that's a pointer to the element at j minus I. So dereference the pointer. Right? And now you have the element at index j minus I. So here's an example using pointer addition and subtraction with an integer value. Right? Okay, so here's my array my array ARR. It's got 7 doubles in it, 0 through 6. Right? I'm going to take a pointer to the third element of the array, so the 3. Right? I'm going to access the element at p plus 2. Right? So if p points at the 3, right, p plus 2 points at the 5. If I dereference that pointer and print it out, I should get 5. Right? So elem is the dereferenced pointer p plus 2. That should print out 5. And it does. Right? What's p minus 3? So p points at the 3. Right? P minus 3 points at 3 elements in front, so it points at the 0. Dereference the pointer, that should give me the 0. And it does. Right? Can I change an element out of the array? You absolutely can. Right? So remember, what is ARR? ARR is a pointer to the first element of the array, so it's a pointer to here. Right? What is ARR plus 6? Well, it's the element at ARR 6, which is here. Right? So if I dereference that pointer, what do I get? I get that element. Right? Can I change its value? You absolutely can. Right? So if I set that element to minus 100, ARR6 becomes minus 100. Right? So using pointer arithmetic, you can access elements of an array just by using the name of the pointer plus adding or subtracting values from the pointer. All right, any questions so far? Okay. Finally, there's something called the too-far pointer in C. So if you have an array of length n, then the C standard guarantees that you can write ARR plus n safely. Right? Now remember, this actually goes one element past the end of the array. Right? If you have an array of size 5, the largest index you can safely use is 4. Right? But ARR plus 5 is not a valid index. Right? However, the language says that pointer actually exists. Right? So in other words, it points at something. You're not allowed to use the something for anything. Right? But it does point at somewhere. It does point somewhere. Right? So it exists. You must not try to dereference that pointer. Right? Again, because you've gone past the end of the array. Right? So the pointer ARR plus n is called the too-far pointer, right? Because it points at the element exactly one past the end of the array, right? And you might wonder why this pointer exists. It's because there's a lot of old C code that relies on this pointer existing. So there's a lot of old C code that iterates over the elements of a list, and it iterates over of an array, and it iterates by advancing a pointer each time, right? In the last iteration of the array, it advances the pointer one past the end of the array and then stops. Right? So the fact that all that old code exists means that the language creators and designers had to ensure that that writing ARR plus n was in fact a valid operation. Right? So you can in fact write ARR plus n. You can even compare two too-far pointers, assuming they point into the same array or past the end of the same array. Right? And those will compare just fine. So in the previous lecture, I mentioned there was this thing called the too-far pointer and that you can compare them. This is why you can compare them, right? It's because there's a lot of existing C code that uses, that relies on this thing existing. Okay, in the last lecture, I also told you you can compare pointers using less than and greater than, right? And so the pointer comparisons only make sense if you have two pointers into the same array. Right? If you have two pointers into different arrays, the comparisons don't make sense anymore. Right? Okay, so you have two pointers P and Q, they point at elements of the same array. Right? Okay, so suppose that P points at array index, the element at ARRI, Q points at ARRJ. Right? And so if you compare the two pointers, what do you know about the elements? So more precisely, what do you know about the location of the elements? So if P is less than Q, right? All that means is that P is pointing at an element in front of Q, right? That is closer to the front of the array than Q. So that means I is less than J, right? So it's pointing at an element ARRI that is before an element ARRJ, right? If P is less than or equal to Q, it means either P and Q are pointing at the same element, or P is pointing at an element in front of the element pointed at by Q. Right? Greater than Q, P greater than Q, this should be obvious now. P points at an element after the element that Q is pointing at. Right? Greater than or equal to Q means that P is pointing at the same element Q is pointing at, or it's pointing at an element after the one that Q is pointing at. Right? So in other words, the comparison operators can be used to compare the locations of two elements that are being pointed at. Right? It doesn't compare their values. Right? So a common mistake here is that you write P is less than Q and you assume, oh, the element that P is pointing at is less than the element that Q is pointing at. Right? That's not correct. If you want to compare the elements, you have to dereference the pointers. Right? So star P less than star Q means the value P is pointing at is less than the value Q is pointing at. Right? P less than Q simply means that P is pointing at an element that comes before Q, the element that Q is pointing at in the array. Okay, so we've got pointer arithmetic, we've got pointer comparison. You can now iterate over an array using pointers. Right? So plus plus, minus minus, plus equals, and minus equals, they do probably what you're hoping they do if you apply them to a pointer. Right? So P plus plus, you have to be careful with P plus plus. P plus plus ends up advancing the pointer P to point at the next element in the array. The thing you have to be careful about is that the value of P plus plus is equal to P. Right? So if you write this somewhere in a statement and you're relying on the value of P plus plus, right? The actual value of P plus plus is P. Right? After you've used the value, P now points at the next element. Right? The same is true of P minus minus. Right? So P minus minus, its value is equal to P. After you've used the value, P now becomes a pointer to the element, in the previous element in the array. Right? That's why they're called post-increment and post-decrement. Right? Post-increment and post-decrement, the value of the thing is equal to its current value. Right? After you've used its current value, it then changes. Pre-increment and pre-decrement, the value of the pointer, the value of P is equal to P plus 1. Right? After you've used its value, the value of P is equal to the old value of P plus 1. Right? Minus minus P means the value of minus minus P is P minus 1. Right? After you've used P, right, the value of P becomes the old value of P minus 1. Right? So P plus equals N means assign the value of P plus N to P. Right? And the result is also P plus N. Right, so if you write P plus equals N, you can actually use that in the middle of a statement somewhere. Right? Its value is equal to P plus N. Right? Similarly, P minus equals N, its value is equal to P minus N. Also causes the value of P to change to become equal to P plus N. Right? So if you want to iterate over an array using a too-far pointer to indicate the end of the array, you can do the following. Right, so here's my array. It has 7 elements in the array. Right, I would like to start at the first element of the array. Right, so a pointer to the first element is just equal to ARR. Right, so notice here my array variable, my loop variable, sorry, is a pointer. Right, so I'm going to take a pointer to the first element of the array. So I can just assign ARR to P. Right. When do I want to stop iterating? Right, well, I want to stop iterating when I hit the element after the 6, right? What is the pointer that's after the 6? It's the too-far pointer, right? It's the element at ARR plus 7, right? 7 elements in the array, right? The too-far pointer is ARR plus 7. So as long as P is less than that value, right? So in other words, as long as it's pointing at this, or this, right? We want the loop to run. Each time that the loop finishes running, we want to advance the pointer to the next element. So you can write P plus plus here. You can write plus plus P here. You can write P plus equals 1 here. They all do the same thing in this case. right? Each time through the loop, I'm simply going to dereference the pointer to get the element being pointed at. Right? So this will print out 0, 1, 2, 3, 4, 5, 6. You can go backwards, right? So I can start at the 6, right? What is a pointer to the 6? It's just ARR plus 6, right? So I can make a pointer, set it to ARR plus 6. That's now pointing at the last element in the array. When do I want this loop to run? Well, as long as P is pointing at an element in the array, right? So in other words, as long as P is greater than or equal to ARR, right? So as long as P is pointing at an element here or further in the array, right? So greater than or equal to ARR. Each time through the loop, I want to move to the previous element in the array, so P minus minus, or minus minus P, or P minus equals 1, right? If you run that code, you get exactly what you expect, right? So going forwards, you get 0, 1, 2, 3, 4, 5, 6, and going backwards, you get 6 down to 0. Right? So if you want to iterate over the elements of an array using a pointer, it's pretty straightforward, right? Start your pointer at the front of the array. Right? Your loop condition is as long as the pointer is not the too far pointer, right? Each time through the array, add 1 to the pointer if you want to go forwards. Right? If you want to go backwards, start at the end of the array. Right? The loop should run as long as P is pointing at a valid element of the array. Right? So as long as it's greater than or equal to ARR. Right? Each time through the loop, decrement the pointer by 1, and that goes backwards. Right? You can count up by 2. Right? That's just P plus equals 2. Right? Or P equals P plus 2. You can count by 3. P equals P plus 3. You can go down in increments of 2 or 3 or whatever you want. Right? So to go down in increments of 2, P equals P minus 2, or P minus equals 2. Okay, I think that's plenty for today. We'll talk about what happens when you pass an array or want to pass an array to a function, or return an array from a function in the next lecture.